Hey everyone, let's jump straight into this explainer. Today we're going to demystify two-dimensional motion and take what looks like scary math and turn it into a really intuitive tool. And we'll do it using a simple, real-world analogy, throwing a ball. Think about it. If you've ever watched a baseball soar through the air, or even just casually tossed a crumpled piece of paper into a wastebasket across the room, you've already witnessed exactly what we're going to break down today.
Here's a quick look at our agenda for today. We'll start with entering the second dimension, move on to Galileo's big secret, then following the perfect arc, and finally, acing the projectile test. And trust me, you'll definitely want to stick around for that final section to get those test answers.
All right, let's kick things off with Section 1, entering the second dimension.
To really get this, imagine sliding a tiny bead back and forth on a straight, rigid wire. That right there is 1D motion. The math is honestly incredibly straightforward because you only have to manage directional changes with simple plus and minus signs. You're moving right, that's a plus. Moving left, that's a minus. Simple. But the second you throw a ball across a yard, you introduce a whole new dimension of complexity. Now you're moving in a plane, horizontally and vertically at the exact same time, and that requires vector algebra and angles.
And this shift perfectly highlights why 2D motion gets a bit trickier. In 1D motion, your velocity and your acceleration are essentially locked together on that exact same straight line. They're either pointing together or fighting directly against each other. But the moment you toss that ball into the second dimension, boom, velocity and acceleration break free from each other. They can suddenly exist at any angle, anywhere from 0 to 180 degrees apart.
So how do we handle this new dimension? Well, physicists use something called the shadow metaphor, which is just brilliant. They take that diagonal motion and break it into pieces. Picture your diagonal throw as casting two completely straight shadows. Imagine a light shining straight down from the ceiling, casting a shadow of the ball on the floor. That represents your horizontal motion, or your x component. Now imagine a light shining horizontally from the side, casting a shadow of that same ball on the wall. That's your vertical motion, the y component. These two shadows are moving simultaneously, and together they create the grand illusion of one complex diagonal throw.
Now this brings us to an absolutely crucial concept we have to define: the vector. It's essentially a geometric tool, an arrow, that lets you lock both the power of your throw, which is the magnitude, and the exact angle of your throw, the direction, into one single package. Think about it like this. Temperature is just a number, but velocity and acceleration, they're vectors. They demand to know not just how much, but which way.
Moving right along, let's dive into Section 2, Galileo's big secret.
So here is a wild, provocative thought from Galileo that literally changes how we view objects in flight. He realized that when you throw a ball, the horizontal forward motion and the vertical falling motion have absolutely zero effect on each other. None. The horizontal axis is completely blind to what the vertical axis is doing, and vice versa. It's like they're living in two totally different worlds. If you were to map out the horizontal motion, you'd see it gliding steadily forward at a constant velocity. Why? Because the horizontal acceleration is zero. But the vertical motion? It's acting exactly like an object in free fall, being constantly pulled down by gravity. So it slows down as it goes up and speeds up as it falls back down. When you combine that steady horizontal glide with that vertical rise and fall, you get that beautiful, perfect parabola shape.
Which leads us perfectly into Section 3, following the perfect arc. Picture a clear, graceful arc of a ball in flight. Now, imagine tracking that flight with a strobe light flashing in a totally dark room at perfectly equal intervals. That flash freezes the ball in time, showing us exactly what those hidden, invisible velocity and acceleration vectors are doing at every single millisecond of the throw.
Let's actually walk through the timeline of this throw. Step 1 is the launch. Bam! Where both the horizontal and vertical velocities are pushing hard. Then we move to Step 2, the mid-ascent. If you visualize the vertical velocity vector, it's getting shorter and shorter as gravity fights it. But here's the crazy part. The horizontal vector stays exactly the same length. Then it hits Step 3, the crucial apex, which we'll dig into in a sec. And finally, Step 4, the descent, where the vertical velocity points downwards and speeds up until it lands. And through that entire journey, the horizontal velocity never changed its speed once.
All right, for all the students out there, pay attention to Section 4, acing the projectile test.
Okay, here is your first classic trap. Physics teachers absolutely love to ask, what happens exactly at the very top of the arc? It really feels like a trick question. But it is purely logical if you just remember that shadow metaphor we talked about earlier. At the absolute peak, the very top of the parabola,
That vertical velocity vector shrinks completely to zero right before the ball begins to fall. For one infinitely small, totally frozen moment, the vertical shadow stops on the wall. The ball is still cruising horizontally, sure, but its vertical speed, exactly zero.
Now for question 2. How does the vertical acceleration change during the ball's flight? This is a great one because it's designed to test if you confuse velocity with acceleration. Intuition tells a lot of folks that acceleration must stop when the ball hits the top of the arc, or maybe it pushes up on the way up and pulls down on the way down.
But actually, the acceleration never changes. Literally, not once. It never changes length, and it never changes direction. It is constantly pointing straight downward at -g, which is the pull of gravity, for the entire flight. Even when the vertical velocity is sitting at 0 at the apex, gravity is still relentlessly pulling perfectly downward. The acceleration is constant from the millisecond it leaves your hand to the second it hits the dirt.
Finally, question 3 asks you to take that conceptual understanding of the apex and turn it into concrete math. How do you calculate the maximum vertical displacement? In other words, how high did the ball actually go?
Well, the formula for maximum height relies completely on what we just established, identifying the exact point where the vertical velocity equals 0. Once you know that the vertical speed vanishes at the absolute top of the arc, you can plug that into basic equations to solve for the height. It is all connected. The conceptual rules we just talked about directly build the mathematical formulas.
So the next time you're outside and you toss a ball across the yard, remember that you aren't just playing a simple game. You are unleashing a beautiful, perfectly predictable set of vectors. You've got horizontal motion gliding constantly forward, completely blind to the vertical motion fighting a constant downward gravity. I challenge you to actually try and visualize those invisible, perpendicular shadow arrows in your own throws. And it makes you think, if this simple, beautiful math governs a baseball, what invisible vectors are currently locking the moon in its orbit around the Earth? Thanks for diving into this explainer with me today. Keep visualizing those vectors, and we'll see you next time.